All right, good morning and happy Friday / Thursday night, everybody. So today we are talking about tree diagrams to measure the number of outcomes that there are within events. So we're going to start off here with a simple event. If we toss a coin 3 times, so over here with me. So we're going to measure the number of outcomes for the first toss, second toss, and our third toss. So, I think we know when we flip a coin, we're going to get one of 2 outcomes. Heads or tails. Every time we flip the coin, we're going to have 2 outcomes, heads or tails. And what we see right here is the principle of making a tree diagram. This is how we can know the number of outcomes an event has. Heads, and I wrote trails. Heads and, you guys can probably hear Shay laughing at me in the back. Heads and tails, heads and trails. Each time. So our third time, we have a possibility of 2 different outcomes one more time. I know I'm not far enough here. I'm gonna go a little bit farther to our third time. We have now 2 outcomes here, heads and tails again. Heads and tails. Let me erase a little bit here. I didn't portion out the space I need well. Heads and tails. And heads and tails. Heads and tails. And for our last 2 outcomes, we have heads.
No marker.
What?
No marker.
I need a different marker. My assistant's telling me heads and tails again. So, everyone's favorite sound. So in a tree diagram like this one right here, we have some options. Now we can do one thing. So if the question is, how many possibilities are there? I'm not going to count this. This is how many possibilities there are for one toss. There's 2. For 2 tosses, there are, I can count 1, 2, 3, and 4 possibilities. On the IXL we're doing today, it's going to ask us how many possibilities there are, how many total possible outcomes there are, and that's always going to be our third column here. 1, 2, 3, 4, 5, 6, 7, and 8 outcomes. There are 8 outcomes. Something else we can do with this is we can label our outcomes. Heads, heads, heads. I would label this one heads, heads. So I'm going here. Heads, 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 and tails. For time's sake, I'm not going to do that all on the board. But the example that we have on the PowerPoint, you guys are going to have this PowerPoint. This is on the agenda here today. You can break down all 8 possible outcomes from 3 heads to 3 tails and everywhere in between using a tree diagram. We're going to do one more example of a tree diagram. This one is a little bit more complicated. We're going to read this real quick. We go out to eat. We can order a hot dog, a burger, and this is going to be the third slide if you guys are following along with this slide too. You can order a hot dog, a burger, or a pizza. So food. We have three options: a hot dog, a burger, or a pizza. To drink, we can have our drink, milk, water, or a soda. Again, with the burger, we could have milk, and I'm just getting this from here. I go and I put my food options, then I put my drink options, milk, water, and soda. You guys may be thinking this is a lot of work. We're going to show you guys a shortcut after this. And for the pizza, we could have milk, water, or soda. Now we have one last option for dessert. That's my favorite sound in the whole world. That's my alarm clock in the morning, true story. So, for dessert, we could have ice cream or cake. I'm just going to put ice cream, cake, ice cream. I'm going to put ice cream or cake, IC or C. I'm just abbreviating here because this is a lot of work. But it's important that we see how the principle works. The tree diagram principle is we can map out all of our different options. These are literally every combination that we could have. A hot dog with soda and cake, or a hot dog with milk and a cake, a burger with water and ice cream, or ice cream would be here. And we would then go in our last row, and I'd count down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18 possibilities. We're not going to actually, on today's practice, ask you guys to use the tree diagram. This principle of what we are doing, we're going to show you the shortcut to get to the end result instead. So the fundamental counting principle. We're going to instead use this on the last one where it wants us to make a tree diagram. The basic idea of the fundamental counting principle is if an event has M is just a variable. It doesn't really mean anything. It just represents the possible outcomes for an event, and another event has N possible outcomes. Those variables just mean numbers. If an event has this many outcomes and another event has this many outcomes, you can multiply. It says you can multiply M and N together, and it'll give you the number of outcomes for the two events or more events together. Let's go back 2 slides to our food example. So food, this might make a little bit more sense in practice. then looking at it with variables. Food has 1, 2, 3 possible outcomes: hot dog, burger, and pizza. Drink options, there is 3: milk, water, and soda. Food times drink times and dessert. Am I spelling dessert or did I spell desert earlier? I don't know.
Desert.
Desert? Oh shoot, not again. Second time this week. So, the basic principle is we multiply the number of outcomes for each event. Our events are food choice, drink choice, and dessert choice, not desert. 3 times 3 times 2. Well, when we did the tree, we saw there were 18 outcomes. 3 times 3 is 9. 3 times 2 is 18. So instead of actually having to make our tree diagram, we can just multiply the number of outcomes by each other. We can, if we want to, make a tree for each of these. It's asking me to make a tree diagram to decide this one. I will probably make a tree diagram for this at the very end of the video just to prove that it'll work for one of these. But what you guys need to do in one of these, because I don't expect you to draw 18 different lines and label everything on something today. All we really have to do is use what we call, on the next slide, the fundamental counting principle. Which all that means is I have to say I have shoes and I have hats. You know what? I'm going to change my mind. I'm going to make a quick tree diagram because this one's going to be short since there's only 2 choices. I have black, white, and red shoes. I want you guys pause your video for a second and take a second and try to finish the tree diagram here. Okay, so now that I did, so you guys had time to do that, we should have finished it something like this. With the black shoes, you could wear a red, blue, black, or tan hat. With the white shoes, you could have worn a red, blue, black, or tan hat. And with the red, you could wear a red, blue, black, or tan hat. So really, what the principle, the tree diagram does is I have 3 options and I break those into 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 options. What if I simply said there's 3 shoe choices times 4 hats? You guys might have seen this pattern when we did the first one with just the coin flips, or the last one too. 3 times 4 is 12. That's how many I count. So what you guys, it's good to know how this works, the tree diagram. All we have to do is multiply the number of outcomes by each other. Could you see that, or was I in front of that entirely? You could see it? Okay. I talk to myself like that too. If she wasn't when I was recording myself, I'd still be asking. So, m times n equals the probability of the 2 events together. That's the fundamental counting principle. But if there are 3 events, let's say m times n, O, M, O, times, I'm going to do p. for the third event, because O looks too much like 0. We don't like to use it as a variable. So if there's 3 events, it would be m times n times p equals m n p, or the possible outcomes, total outcomes. So no matter how many events you guys have on the IXL today, you might see up to, I think, 4 events. Unless you go for above 70%, then you could see more. If you had 4 events, you would just multiply like m times n. And again, these are just variables. This means probability of event 1, event 2. This is event 1, 2, and 3 times p, which is 3. LMNOPQ. I know the alphabet. I teach math, not English. I'm sorry. Q would be event 4. So if you had 4 events, you'd multiply the first, second, third, and fourth event number of outcomes together. That gets you total outcomes. So no matter how many outcomes there are, if you multiply the number of outcomes from each event, so no matter how many events there are, if I multiply the number of outcomes from event 1 by 2, by 3, by 4, that'll always give me the total number of outcomes. Okay, so let's read this one real quick. Let's see, what happens if I put this on here? Can you see this? I want to, does that show up on your camera?
Yeah.
I want to be able to show, when I see this many words, this one looks a little bit more difficult. Oh, what's our time count right now?
17 minutes.
17. So I'm going to wrap this up shortly. Kara went to the Southside Soda Shop for lunch yesterday. She had a choice of soda or juice to drink. So drink choice. For the drink choice, there are 2 options. Her sandwich could be a bagel or white bread. So sandwich, I see 2 options. And her choice of cheese, roast beef, or turkey. So for, I don't know what to say for that. Let's say protein. She has 3 options. 2 times 2, 2 juice or drink options, 2 bread options, and 3, we're going to say protein options. 2 times 2 times 3. 4 times 3 is 12. We could make the whole tree diagram. Can you pause it for a second and I'll create it? Is it paused? Is it hitting play yet or not?
Yes.
Oh my gosh. Okay, so bringing it back in here. I made this just a second ago. I didn't want to have to bore you guys with me making it, but all I do is, for my drink options, I put my 2. For my sandwich options, I branch those out into my options. And for, I'm calling it protein options, I branched or treed out into cheese, roast beef, turkey, cheese, roast beef, turkey. So in the end, I have, these are my different options. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's what we got when we simply multiplied 2 times 2 times 3. So our tree diagram that we can create here, we don't really have to do it, but we should understand why it works. And if somebody asks me to make one, I don't think we're gonna plan on asking you guys to make one of these on any of our quizzes we're going to do outside of school, but it's a good idea to just know what it means. I take choice 1 and I split it into my 2 options, a drink being a soda or a juice. Choice 2, split it into bagel and bread for each of these choices. And now I have 1, 2, 3, 4 choices. Each of those 4 choices I split into the remaining 3 to give me 12. That's why 2 times 2 times 3 works. Here I split it twice. Here I split it twice. And here I split it 3 times for each of the ones that's before it. That's what we actually do here. So I'm going to do one last problem here. I think we're gonna skip this one. And I'm gonna find a little bit more difficult problem. Okay, so let's look at this. We have bread, cheese, and meat. There are 1, 2, 3, and 4 bread options. 1 and 2 cheese options, and 1, 2, 3, and 4 meat options. So I just need to figure out how many options do I have and for how many categories. 4 times 2 times 4. 4 times 2 is 8. 8 times 4, 32 outcomes. So I'm going to end this lecture really here. We've gone over the tree diagram. So we're going to look at the tree diagram. Sorry to go way back here. But our tree diagram is basically just this. For each event, I'm going to break it down. For the first event, I break it down into the total possible outcomes. Then the second event, I break it down into the total outcomes. And for the third event, I break it down into the total outcomes. This whole slide is shared with you guys. Now, we've got everything broken down, and we can count our outcomes. We could list the actual outcomes. 3 heads. The first 2 are heads and the tails. Heads, tails, heads. Heads, tails, tails. Tails, heads, heads. Tails, head, tails. Tails, tails, head. And tails, tails, tails. That's the benefit of the whole tree diagram, is it really gives us a full understanding of what's going on. The other thing we learned is the counting principle. In the counting principle, I take, for the first event, there's 2 outcomes. For the second event, there's 2 outcomes. And for the third event, there's 2 outcomes. When I multiply that together, 2 times 2 is 4, times 2 is 8. I had 1, 2, 3, 4, 5, 6, 7, and 8. So we learned 2 different ways to get to the same place. When in doubt, if you're not sure, make a tree diagram. But with the fundamental counting principle, I know that I just have to multiply the number of outcomes for each event to get my total outcomes. I'm going to post another video shortly that'll have just a couple examples from the IXL on it. If you don't need help with the IXL, don't bother watching it. Okay, thank you guys. If you have any questions, email me.
Do a dance.